Welcome to the Midnight Sleep Scientist, a place where you can let the day drift away as you settle in for the night. Tonight's journey takes us far beyond the familiar realm of matter and light, into the deepest mysteries of space and time, where invisible titans dance in the darkness, slowly spiraling toward encounters that shake the very fabric of reality itself. Before we begin, may I ask, where are you listening from this evening? Whether you're curled up in bed, resting on the sofa, or gazing out at the night sky, I'm glad you're here. If you find these calming explorations helpful, a like and a subscribe would mean a lot. And for those already subscribed, thank you for being part of this quiet voyage through the universe. I'll do my best not to keep you awake, but if you happen to stay up a little longer, at least you'll leave with a few new wonders tucked into your mind. So as your eyes grow heavy, let's begin our journey. After all, what really happens when two black holes collide? Collisions in the cosmos may sound violent, yet when it comes to black holes, they unfold with a majesty that defies imagination. These are not explosive crashes, but slow gravitational waltzes that play out across millions of years, ending in moments so brief, yet so powerful that they send ripples through the universe itself. Black holes, the most enigmatic objects in existence, are regions where gravity has become so intense that nothing, not even light, can escape their grasp. Yet when two of these cosmic phantoms find each other in the vast darkness, their meeting becomes one of the most spectacular events the universe can produce. In this exploration, you'll discover how these invisible dancers find their partners across the emptiness of space, how they slowly spiral together in an embrace that reshapes the very geometry of reality, and what happens in that final moment when two black holes become one. We will journey through the physics of space-time itself, explore the gravitational waves that carry news of these distant encounters to Earth, and look ahead to the future collisions that await in the deep cosmos. These stories unfold not in human time, but in the patient rhythms of the universe itself, where millions of years pass like seasons, and the most violent events occur with a grace that can only be described as cosmic poetry. Because within these collisions lies a reminder that even the darkest, most mysterious objects in the universe participate in a grand dance, one that connects the smallest ripples in space-time to the largest structures in the cosmos, showing us that everything, even the void itself, is alive with motion and meaning. If you could step far enough outside our solar system, beyond the reach of the sun's light, beyond the glow of nearby stars, you would find yourself in a realm where the familiar rules of physics begin to bend and twist. Here, in the deep darkness between galaxies, lurk objects so dense and powerful that they challenge our very understanding of reality. These are black holes, regions of space-time where gravity has become so intense that the normal flow of cause and effect breaks down, where time itself slows to a crawl, and where the boundary between existence and nothingness becomes razor thin. A black hole is not quite a hole in the traditional sense, though the name has endured since it was coined by physicist John Wheeler in 19. It is better understood as a region of space where matter has collapsed so completely that it warps the fabric of space-time itself into an inescapable well. Imagine the surface of a trampoline stretched tight, then picture dropping a bowling ball into its center. The fabric curves downward, creating a depression that grows deeper and steeper toward the center. Now imagine that depression becoming so deep and steep that anything rolling toward it would inevitably fall in, never to return. That is the essence of a black hole, except instead of a trampoline, it is the four-dimensional fabric of space-time that curves, and instead of a bowling ball, it is matter compressed beyond all imagination. At the heart of every black hole lies a singularity, a point where matter is crushed to infinite density, and the curvature of space-time becomes infinite. This is not merely a very small object, but a place where the very concepts of size, shape, and even existence lose their meaning. The singularity is surrounded by the event horizon, an invisible boundary that marks the point of no return. Cross this threshold and not even light traveling at 300,000 kilometers per second can escape the black hole's gravitational embrace. The event horizon is not a physical surface you could touch, but rather a mathematical boundary in space-time itself, a one-way membrane that allows matter and energy to fall in but never to emerge. Black holes come in several varieties, each with its own personality and history. The most common are stellar black holes, born from the deaths of massive stars. When a star at least 20 or 30 times more massive than our Sun exhausted its nuclear fuel, gravity finally overwhelms all other forces. The star's core collapses in less than a second, creating a black hole with a mass several times that of the Sun, but compressed into a sphere only a few dozen kilometers across. These stellar black holes are scattered throughout galaxies like invisible seeds, most of them solitary and quiet, detectable only when they happen to steal matter from a nearby companion star. Then there are the intermediate black holes, objects with masses between stellar black holes and their giant cousins. These remain somewhat mysterious, as they are difficult to detect and their formation mechanisms are not fully understood. They may form when stellar black holes merge, or perhaps they are the remnants of the first generation of stars in the early universe. Like the middle children of the black hole family, they are often overlooked, but they may play crucial roles in the cosmic hierarchy. At the other extreme are the supermassive black holes, monsters with masses millions or billions of times greater than the Sun. These titans lurk at the centers of most galaxies, including our own Milky Way, where a supermassive black hole called Sagittarius A weighs in at about 4 million solar masses. Despite their enormous bulk, even these giants are surprisingly compact. A supermassive black hole with the mass of 1 billion suns would have an event horizon roughly the size of our solar system, making it incredibly dense by any standard. What makes black holes truly extraordinary is not just their immense gravity, but the way they warp the very nature of space and time. Near a black hole, time passes more slowly relative to distant observers, an effect predicted by Einstein's general theory of relativity. If you could watch someone falling toward a black hole from a safe distance, you would see their clocks running slower and slower as they approached the event horizon. From your perspective, they would appear to freeze just at the edge, their image growing redder and fainter until it faded from view. Yet from the falling person's perspective, they would cross the event horizon in finite time, continuing their journey toward the central singularity. This warping of time and space becomes even more pronounced when black holes spin, as most of them do. A rotating black hole drags space-time around with it in a phenomenon called frame dragging, creating a region called the ergosphere, where space itself is pulled along with the black hole's rotation. Within this region, it becomes impossible to remain stationary relative to distant stars, as the very fabric of space is flowing like a river toward the black hole's equator. Black holes are also characterized by their temperature, though this might seem contradictory for objects that absorb everything and emit nothing. Quantum mechanics tells us that black holes actually do emit radiation, known as Hawking radiation, after physicist Stephen Hawking, who first described it. This radiation is incredibly faint for astronomical black holes, with larger black holes being colder than the cosmic microwave background. A stellar black hole has a temperature of only a few billionths of a degree above absolute zero, while a supermassive black hole is even colder. This radiation is so weak that it would take longer than the current age of the universe for even a stellar black hole to evaporate completely through this process. The formation of black holes is itself a story of cosmic violence and beauty. When a massive star runs out of fuel, the nuclear furnace in its core shuts down, and gravity finally wins its long battle against the outward pressure of radiation. The core collapses catastrophically, compressing matter beyond the point where even neutrons can support the weight. In less than a second, a region that once spanned thousands of kilometers is crushed down to a point. The outer layers of the star rebound off this collapse and are hurled into space in a supernova explosion that can briefly outshine an entire galaxy. Yet for all their reputation as cosmic destroyers, black holes are also creators. They shape the formation and evolution of galaxies, regulate star formation through their gravitational influence, and when they feed on surrounding matter, they can become among the brightest objects in the universe. As matter spirals into a black hole, it forms an accretion disk, heating to millions of degrees, and shining brilliantly across the electromagnetic spectrum. Some black holes launch powerful jets of particles that extend for thousands of light years, carving cavities in the surrounding gas and influencing star formation across vast regions of space. Black holes also serve as natural laboratories for testing our most fundamental theories of physics. They represent the extreme limits where general relativity and quantum mechanics must somehow be reconciled, pointing toward a deeper understanding of the universe. In their event horizons, we glimpse the boundary between the known and the unknowable. In their singularities, we encounter the limits of physics itself. To contemplate a black hole is to face the profound mystery of existence itself. These objects challenge our intuitions about space, time, matter, and causality. They remind us that the universe contains realms so extreme that they stretch human comprehension to its limits. Yet in their mathematical beauty and their role in shaping the cosmos, black holes also reveal the elegant underlying order that governs reality, even at its most extreme edges. When astronomers first began to contemplate the possibility of such objects, they seemed almost too strange to exist. The idea that matter could collapse so completely that it would disappear from the observable universe was both fascinating and terrifying. Today we know that black holes are not only real but fundamental to the architecture of the cosmos. They are the periods at the ends of stellar sentences, the seeds around which galaxies grow, and the subjects of some of the most beautiful equations in physics. In the darkness between stars, black holes wait with infinite patience. They are not malevolent devourers, as popular culture sometimes portrays them, but natural consequences of the laws of physics playing out on the grandest stages. They represent both endings and beginnings, destruction and creation, the finite and the infinite, all wrapped together in objects so compact they could fit within the orbit of Mercury, yet so influential they shape the evolution of entire galaxies. Understanding black holes is understanding the universe at its most fundamental level, where space and time are not fixed stages, but dynamic players in the cosmic drama. These invisible titans, scattered throughout the universe like punctuation marks in the story of creation, await encounters with their own kind, encounters that will reveal some of the deepest secrets of reality itself. To understand what happens when black holes collide, we must first venture into one of the most profound discoveries in the history of science, the realization that space and time are not separate, unchanging backdrops against which the universe plays out its drama, but are instead woven together into a single dynamic fabric that can bend, stretch, and ripple like the surface of a vast cosmic ocean. This fabric, which physicists call spacetime, is not just the arena where physics happens. It is an active participant in every gravitational interaction, every orbit, every collision, and every wave that propagates across the cosmos. But Einstein's greatest triumph came 10 years later with his general theory of relativity, which revealed that gravity itself is nothing more than the curvature of spacetime. Massive objects don't pull on other objects across empty space, as Newton had imagined. Instead, they warp the geometry of spacetime itself, creating curves and valleys that guide the motion of everything around them. A planet orbiting a star is not being pulled by a mysterious force, but simply following the straightest possible path through curved spacetime, what mathematicians call a geodesic. The story begins with Albert Einstein, who in 1905 overturned our common sense notions of space and time with his special theory of relativity. Einstein showed that there is no universal now that applies everywhere in the universe. Instead, the flow of time depends on your motion and your position in gravitational fields. A clock moving at high speed runs slower than a stationary one, and a clock deep in a gravitational well ticks more slowly than one farther away. Space and time, Einstein realized, are intimately connected. They form a four-dimensional continuum where the three dimensions of space and the one dimension of time are inextricably intertwined. Imagine space-time as a vast rubber sheet stretched in all directions. Place a heavy marble in the center, and the sheet dimples downward, creating a depression. Now roll smaller marbles nearby, and they will naturally curve around the depression. following paths that appear to be orbits from our perspective. The larger the central mass, the deeper the depression, and the more dramatically the smaller objects curve around it. This analogy, while imperfect, captures the essence of how mass and energy curve spacetime, and how that curvature guides the motion of matter and energy. Black holes represent the extreme limit of this curvature. They are places where the rubber sheet of spacetime is not merely dimpled, but stretched so severely that it forms an infinite funnel, a geometric trap from which nothing can escape. The mathematics that describes this curvature is both beautiful and terrifying. Equations that speak of horizons beyond, which cause and effect break down, of singularities, where the curvature becomes infinite, and of regions where time itself seems to stop. The geometry around a black hole is described by the Schwarzschild metric, named after Karl Schwarzschild, who found the solution to Einstein's equations just months after general relativity was published, and tragically just before he died on the Russian front during World War I. The Schwarzschild metric describes the space-time around a non-rotating black hole, revealing how time slows down and distances stretch as you approach the event horizon. According to this metric, an outside observer watching someone fall into a black hole would see their image frozen forever at the horizon, growing dimmer and redder but never quite disappearing. For rotating black holes, which includes virtually all real black holes, the situation becomes even more complex. The solution to Einstein's equations for a spinning black hole, found by Roy Kerr in 1963, describes a space-time geometry where the rotation of mass energy drags space and time around with it. This frame-dragging effect means that near a rotating black hole, space itself is flowing like honey, making it impossible to remain stationary relative to distant stars. The faster the black hole spins, the more severe this dragging becomes, creating an ergosphere, a region where space-time itself is forced to rotate along with the black hole. Within this curved space-time, some of the most counterintuitive phenomena in physics unfold. Time dilation near black holes is not merely a theoretical curiosity, but a measurable effect that must be accounted for in precise astronomical observations. Light climbing out of a gravitational well loses energy and becomes redshifted, while light falling in gains energy and becomes blue-shifted. These effects become extreme near black holes, where photons climbing away from the event horizon can lose most of their energy, effectively disappearing from view. The curvature of space-time around black holes also bends the paths of light rays, creating gravitational lensing effects that can magnify, distort, and multiply the images of objects behind them. This lensing can be so strong that light can orbit around a black hole multiple times before escaping, creating what physicists call photon spheres, ghost-like regions where light can circle endlessly just outside the event horizon. But perhaps the most remarkable property of spacetime is that it can carry waves. Just as a stone dropped in a still pond creates ripples that spread outward across the water's surface, accelerating masses can create ripples in spacetime itself, gravitational waves that propagate at the speed of light, carrying information about the violent events that created them. These waves represent oscillations in the geometry of space and time themselves, alternately stretching and compressing distances as they pass through matter. Einstein himself was skeptical about whether gravitational waves really existed or were merely mathematical artifacts of his theory. The waves are extraordinarily weak. Even the most violent cosmic events produce ripples that stretch space by amounts far smaller than the nucleus of an atom. For decades they remained purely theoretical, predicted by the equations but beyond any hope of direct detection. The mathematics of gravitational waves reveals that they are produced most efficiently by asymmetric accelerations of mass energy. A perfectly symmetric explosion produces no gravitational waves, but two masses orbiting each other create a constantly changing quadrupole moment that radiates energy in the form of space-time ripples. The more massive the objects and the more compact their orbit, the stronger the waves they produce. The geometry of space-time during such mergers becomes extraordinarily complex. As two black holes spiral together, their individual event horizons begin to distort and stretch toward each other. At the moment of merger, a new, larger event horizon forms around both black holes, and the space-time geometry settles into a new equilibrium state, described by the mathematics of general relativity. The process is both destructive and creative. Two separate black holes cease to exist as individual entities, but a new, larger black hole is born from their union. As gravitational waves carry energy away from an orbiting system, the orbit gradually decays. The two objects spiral closer together, orbiting faster and faster, producing stronger and stronger waves in an accelerating feedback loop. This in-spiral continues until the objects merge, producing a final burst of gravitational radiation, so intense that it can briefly outshine all the ordinary matter in the observable universe, though this energy emerges not as light, but as ripples in space-time itself. The detection of gravitational waves has opened an entirely new window on the universe, allowing us to observe events that produce no light, no heat, no electromagnetic radiation of any kind. When two black holes merge in a distant galaxy, they can remain completely invisible to conventional telescopes. Yet their collision sends gravitational waves racing across the cosmos at the speed of light. These waves carry information encoded in their frequency and amplitude about the masses of the merging objects, their spins, their orbital characteristics, and even their distance from Earth. The space-time around merging black holes becomes a laboratory for testing general relativity in its most extreme regime. The enormous gravitational fields and high velocities involved push Einstein's theory to its limits, providing tests of physics that are impossible to replicate in any terrestrial laboratory. So far, every observation has confirmed Einstein's predictions with remarkable precision, validating our understanding of space-time even in these most extreme environments. To visualize the collision of two black holes is to imagine space-time itself engaged in a violent dance. The normally smooth geometry becomes turbulent, with waves of curvature propagating outward like ripples on a storm-tossed sea. The event horizons, those boundaries beyond which even light cannot escape, merge and reshape themselves according to the intricate mathematics of general relativity. Space stretches and contracts, time dilates and compresses, and the very fabric of reality trembles with the energy of the encounter. Yet for all their violence, these collisions unfold according to precise mathematical laws, following geodesics through curved space-time with the same inevitability that planets follow their orbits around stars. The chaos is only apparent. Beneath the turbulent surface lies the elegant order of Einstein's field equations, describing with mathematical precision how matter and energy curve space-time and how that curvature guides the motion of matter and energy in return. In the end, the physics of space-time reveals black hole collisions to be not merely violent encounters between massive objects, but fundamental transformations in the geometry of reality itself. They are events where space and time become the primary players, where the invisible architecture of the universe reveals itself through gravitational waves that carry the news of distant catastrophes across billions of years and billions of light years to sensitive detectors on Earth. In studying these collisions, we are not merely observing distant astronomical events, but probing the very nature of existence itself, exploring the deepest foundations upon which all of reality is built. In the vast emptiness between stars, where space seems silent and still, the most extraordinary partnerships in the universe slowly unfold. Binary black hole systems, two invisible titans locked in gravitational embrace, perform dances that last millions of years, spiraling ever closer in orbits that gradually tighten with each revolution. These are not chance encounters, but relationships written into the fabric of space and time itself, guided by the patient mathematics of orbital mechanics and the inexorable pull of gravity. The formation of binary black hole systems tells a story that stretches back billions of years. Most begin their lives not as black holes, but as massive binary star systems, two stellar giants orbiting their common center of mass in a cosmic waltz that may have lasted for millions of years. These stellar partners were born from the same cloud of gas and dust, grew up together in the same stellar nursery, and lived their lives in orbital synchronization. Each star's evolution influenced by the gravitational pull and sometimes the mass transfer from its companion. When stars this massive exhaust their nuclear fuel, their deaths are spectacular. In less than a second, the core of each star collapses beyond the point where even neutrons can support its weight, forming a black hole, while the outer layers explode outward in a supernova that briefly outshines entire galaxies. For a binary system to survive this double catastrophe and emerge as a pair of black holes still bound to each other is remarkable enough to be almost miraculous. The violent asymmetry of each supernova explosion imparts powerful kicks to the newly formed black holes, often flinging them apart at speeds of hundreds of kilometers per second. Yet sometimes, against all odds, the gravitational bond survives. The two black holes, now invisible and nearly indestructible, continue their orbital dance, though their relationship has fundamentally changed. Where once they were luminous stars that could heat planets and drive stellar winds, they are now defined purely by their gravitational influence, invisible curves in space-time that betray their presence only through their effects on nearby matter, and on each other. The orbital dynamics of binary black holes follow the same basic principles that govern any gravitational system, but with complications that arise from the extreme warping of space-time in their vicinity. Unlike planets orbiting a star, where one body is much more massive than the other, binary black holes often have comparable masses, creating a true partnership where both objects orbit around their mutual center of mass, called the barycenter. These orbits begin wide and elliptical, with the black holes separated by distances that may span several times the diameter of our solar system. At such distances, their orbital periods stretch across thousands of years, and their gravitational interaction follows the familiar inverse square law that Newton discovered centuries ago. The black holes chase each other through space with the patience of cosmic clockwork, their positions predictable far into the future by the mathematics of celestial mechanics. But binary black holes possess a unique property that sets them apart from ordinary orbital systems. They radiate energy in the form of gravitational waves. As they orbit each other, their acceleration creates ripples in spacetime that carry energy away from the system at the speed of light. This energy loss is incredibly small at first, far too small to be measured by any conceivable instrument, but it has a cumulative effect that builds over millions of years. The radiation of gravitational waves causes the orbit to decay almost imperceptibly at first. The black holes drift closer together by distances smaller than the width of atomic nuclei each year. Changes so tiny they would be unnoticeable even if you could watch the system directly. But as the orbit shrinks, the black holes move faster, and faster moving accelerating masses radiate gravitational waves more efficiently. The energy loss accelerates, the orbit decays more rapidly, and the system enters a gradually accelerating death spiral. This process, known as in-spiral, follows a predictable mathematical progression. The closer the black holes get, the faster they orbit, and the more energy they radiate away as gravitational waves. What begins as an imperceptible drift lasting millions of years eventually becomes a runaway process. In the final minutes before merger, the black holes are orbiting each other hundreds of times per second, their event horizons nearly touching, their combined gravitational field creating distortions in spacetime so severe that they can be detected by instruments on Earth from billions of light years away. The gravitational waves themselves carry the signature of this in-spiral, encoding information about the masses of the black holes, their spins, the eccentricity of their orbit, and their distance from Earth. As the waves pass through space, they alternately stretch and compress distances in directions perpendicular to their travel, creating oscillations that follow a distinctive pattern called a chirp, a gradual increase in frequency and amplitude that reflects the accelerating spiral of the black holes toward their final merger. The mechanics of this in-spiral are governed by the post-Newtonian approximation, a mathematical framework that extends Newton's laws of gravity to account for effects predicted by general relativity. These calculations reveal that the rate of energy loss depends on the masses of the black holes and their orbital separation, according to precise mathematical relationships. The total energy radiated away during the entire inspiral can amount to several percent of the combined mass of the black holes, converted directly into gravitational radiation, according to Einstein's famous equation, EmC quadrate. As the black holes spiral inward, their orbital dynamics become increasingly complex. The intense gravitational fields they create begin to significantly warp the spacetime through which they move, causing relativistic effects that have no analogue in Newtonian mechanics. Their orbit begins to precess, rotating slowly like the orbit of Mercury around the Sun, but much more dramatically. The black holes themselves may be spinning rapidly, and these spins interact with the orbital motion through spin-orbit coupling, causing the orbital plane to wobble and the spins to gradually align with the orbital angular momentum. The approach toward merger also involves tidal effects that have no parallel in ordinary matter. As the black holes draw close enough that their event horizons begin to distort, the boundaries of no return themselves start to stretch toward each other like cosmic teardrops. The precise shape of these distorted horizons depends on the masses and spins of the black holes and provides crucial information about the final moments before merger. In systems where the masses are significantly different, one black hole much larger than the other, the smaller black hole gradually spirals into the larger one in a process reminiscent of a whirlpool consuming a smaller eddy. The dynamics are asymmetric, with the smaller black hole following an increasingly tight spiral path around its massive companion until it finally disappears beyond the larger black hole's event horizon. When the masses are more nearly equal, the final approach becomes a complex gravitational choreography, where both black holes dance around their common center of mass in ever-tightening loops. The space-time geometry becomes so severely warped that conventional notions of orbital mechanics break down, and only the full machinery of general relativity can accurately describe what happens next. Throughout this entire process, which may span millions of years from the initial pairing to the final moments before merger, the binary system remains completely invisible to ordinary telescopes. Unlike stars or galaxies, which shine with the light of billions of suns, black holes in empty space emit no electromagnetic radiation. Their presence can be inferred only through gravitational effects, the way they bend light from more distant objects, or the gravitational waves they emit as they spiral together. The binary dance is a testament to the patience of the universe. Forces that seem impossibly weak can, given enough time, produce the most dramatic consequences. The energy carried away by gravitational waves is unimaginably small compared to the total mass energy of the black holes, yet over millions of years it is enough to bring them from vast separation to intimate contact. This gradual inspiral also represents one of the most precise confirmations of Einstein's general theory of relativity. The rate at which binary systems lose energy to gravitational radiation was first measured indirectly in the famous Hulse-Taylor binary pulsar, where two neutron stars orbit each other with precisely the orbital decay predicted by general relativity. The discovery earned Russell Hulse and Joseph Taylor the Nobel Prize in Physics and provided the first indirect evidence for the existence of gravitational waves. For binary black holes, the inspiral phase represents the calm before the storm. The gradual spiral inward, lasting millions of years, is merely the prologue to one of the most violent events in the universe, the final merger and ringdown that will reshape space-time itself and send gravitational waves racing across the cosmos with the news of this cosmic catastrophe. The binary dance, for all its patient beauty, is ultimately a countdown to one of the most spectacular collisions nature can produce. As two black holes spiral ever closer in their gravitational dance, they approach a threshold where the familiar laws of orbital mechanics give way to something far more exotic. In the final moments before merger, space-time itself becomes a turbulent sea, stretching and compressing in ways that challenge our most sophisticated mathematical descriptions. These are not the gentle, predictable motions of planets around stars, but violent fluctuations in the very geometry of reality, oscillations so extreme they momentarily outshine all the ordinary matter in the observable universe, though they do so not with light, but with ripples in space and time themselves. The final phase begins when the black holes are separated by only a few times their own diameter, a distance that, despite sounding small, still represents hundreds or thousands of kilometers. At this separation, they are orbiting each other so rapidly that they complete dozens of revolutions each second. The gravitational waves they emit have grown strong enough to carry away enormous amounts of energy, causing the orbit to decay not over millennia, but over minutes and seconds. During these final moments, the black holes are moving at significant fractions of the speed of light, creating relativistic effects that have no parallel in everyday experience. As they race around each other in their death spiral, the Doppler effect causes the gravitational waves they emit to sweep across the sky like lighthouse beams, creating complex interference patterns as waves from different parts of the orbit overlap and combine. The event horizons, those invisible boundaries beyond which nothing can escape, begin to deform dramatically as the black holes approach. What were once perfect spheres become elongated teardrops, stretching toward each other as the tidal forces intensify. These distortions grow more pronounced with each orbit, until the horizons develop narrow bridges that reach across the shrinking gap between the black holes. The mathematics describing these final moments requires the full power of numerical relativity, computer simulations that solve Einstein's field equations using some of the most powerful supercomputers on Earth. The equations are so complex that they resisted solution for decades, requiring the development of new computational techniques and enormous advances in computing power before the first successful simulations were achieved in 2005. These simulations reveal that the merger itself happens with startling suddenness. After millions of years of gradual in-spiral, the actual collision lasts only a few milliseconds. In that brief time, the two separate event horizons merge into a single, larger horizon that initially oscillates wildly before settling into the smooth geometry of a single, more massive black hole. The moment of merger is preceded by a final burst of orbital acceleration as the black holes complete their last few revolutions. The gravitational waves emitted during this phase sweep upward in frequency like a cosmic siren, growing stronger and stronger until they reach a crescendo at the instant of collision. The total energy radiated during the final second before merger can exceed the luminous energy output of all stars in the observable universe combined, though this energy emerges as invisible gravitational radiation rather than light. At the moment of contact, when the event horizons finally touch, the two black holes cease to exist as separate entities. The merger is not a gradual blending, but an instantaneous transition. One moment there are two black holes, the next there is one. The physics of this transition involves concepts at the very edge of our understanding, where quantum mechanics and general relativity meet in ways that are still being explored by theoretical physicists. The newly formed black hole that emerges from this collision is typically less massive than the sum of its parents. The missing mass has been converted directly into gravitational wave energy and radiated away into space, following Einstein's famous relationship EMC quadrate. For typical stellar mass black hole mergers, the equivalent of several solar masses can be converted into pure gravitational radiation in the final fraction of a second before merger. But the violence does not end with the merger itself. The newly formed black hole is born in a highly disturbed state, its event horizon oscillating like a struck bell as it settles into equilibrium. This ring-down phase produces its own characteristic pattern of gravitational waves, with frequencies and decay rates determined by the mass and spin of the final black hole. These oscillations are described by the mathematics of black hole perturbation theory, which reveals that black holes can vibrate in specific modes, each with its own characteristic frequency, like the harmonics of a musical instrument. The ring-down radiation provides a direct probe of the final black hole's properties. By measuring the frequencies and decay rates of these oscillations, astronomers can determine the mass and angular momentum of the merger product, providing a test of general relativity's predictions about black hole dynamics. So far, every observed merger has produced ring-down signals that match Einstein's theory with remarkable precision. During the merger and ring-down phases, the black hole system radiates gravitational waves with peak power outputs that can exceed 1023 watts, more power than is contained in all the starlight from all the galaxies in the observable universe. Yet, because gravitational waves interact so weakly with matter, this enormous flux of energy passes through planets, stars, and entire galaxies as if they weren't there, carrying information about the collision across billions of light years with almost no attenuation. The gravitational waves from black hole mergers encode detailed information about the colliding objects. The early inspiral phase reveals the individual masses of the black holes and provides constraints on their spins. The merger phase encodes information about the dynamics of highly curved spacetime, while the ring-down phase directly probes the properties of the final black hole. This wealth of information makes gravitational wave astronomy a powerful tool for studying black hole physics and testing general relativity in its most extreme regime. The waveforms produced by black hole mergers follow distinctive patterns that depend on the masses and spins of the colliding objects. Equal mass mergers produce relatively symmetric waveforms, while systems with very different masses create more complex signals as the smaller black hole spirals into the larger one. Rapidly spinning black holes generate different waveforms than slowly rotating ones, and the relative orientation of the spins affects the dynamics of the merger in subtle but measurable ways. These final moments also provide insights into the formation and evolution of binary black hole systems. The properties of the gravitational waves reveal not only what the black holes are doing during the collision, but also clues about their entire previous history, how they formed, whether they were born as a binary or captured each other later, and what kinds of stellar evolution produced them in the first place. The detection of these signals on Earth requires extraordinary precision. The gravitational waves from even the most powerful black hole mergers stretch space by amounts smaller than 1/10,000th the width of a proton when they reach our planet. Detecting such tiny distortions requires laser interferometers with arm lengths of several kilometers, and isolation systems that can eliminate vibrations from sources as diverse as seismic activity, passing trucks, and even quantum fluctuations in the light itself. When such a signal is detected, it represents the culmination of a process that began millions of years ago, when two massive stars first started their gravitational dance. The final moments of merger, lasting only seconds, are the climax of an epic that spans the evolution of stars, the dynamics of binary systems, and the propagation of gravitational waves across cosmic distances. In those brief seconds, two of the most mysterious objects in the universe unite to create something new, sending ripples through spacetime that carry the news of their collision to every corner of the cosmos. The aftermath of merger leaves behind a single black hole, typically more massive than either of its progenitors, but slightly less massive than their combined original mass. This difference represents the energy that escaped as gravitational waves, a direct conversion of mass into pure space-time curvature that propagates outward at light speed. The newly formed black hole settles into equilibrium over the course of milliseconds, its final mass and spin determined by the conservation laws that govern all such encounters. In the moments following merger, as the gravitational wave signal fades to silence, the merged black hole begins its solitary existence. It may find itself in a region of space stripped bare by the violence of the collision, with any nearby matter scattered by the gravitational disruption. Or it may inherit an environment rich in gas and dust, material that will slowly spiral inward over millions of years, occasionally flaring as it heats up and glows before disappearing forever beyond the event horizon. In September 2015, humanity achieved something that would have seemed like magic to previous generations. We learned to feel the universe trembling. On that day, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected the faint whisper of space-time itself, oscillating as gravitational waves from a black hole collision 1.3 billion years ago finally reached Earth. In that moment, we gained a new sense, the ability to perceive not just the light of distant stars, but the actual geometry of space and time as it stretches and compresses around us. Gravitational waves are perhaps the most elusive prediction of Einstein's general theory of relativity. Unlike electromagnetic waves, which are oscillations in electric and magnetic fields, gravitational waves are oscillations in the fabric of space-time itself. They represent the dynamic aspect of gravity, the way that accelerating masses can shake the very foundation of reality, sending ripples outward that carry energy and information across the cosmos at the speed of light. To understand gravitational waves, imagine space-time as a vast three-dimensional spiderweb stretched in all directions. When something massive accelerates, particularly when it accelerates asymmetrically, it creates vibrations in this web that propagate outward like ripples on a pond. But unlike ripples in water, these disturbances affect the distances between all objects they pass through, alternately stretching space in one direction while compressing it in the perpendicular direction. The waves themselves are incredibly weak. Even the most violent cosmic catastrophes produce ripples that by the time they reach Earth change distances by amounts far smaller than the nucleus of an atom. A gravitational wave stretches the distance between you and the nearest star by less than the width of a single proton. This extraordinary weakness is why gravitational waves remained purely theoretical for a century after Einstein first predicted their existence. Einstein himself had doubts about whether gravitational waves were real physical phenomena or merely mathematical artifacts of his theory. In 1936, he and his collaborator Nathan Rosen even wrote a paper arguing that gravitational waves didn't exist, though they later withdrew this claim. The mathematics was subtle, and it took decades of theoretical work to establish definitively that the waves carried real energy and could, in principle, be detected. The first indirect evidence for gravitational waves came from observations of the Hulse-Taylor binary pulsar, discovered in 19... This system consists of two neutron stars orbiting each other every 8 hours, one of which is a pulsar that sweeps radio beams across Earth with the precision of an atomic clock. By timing the arrival of these pulses over many years, astronomers could measure the orbital decay of the system with extraordinary accuracy. What they found was that the orbit was shrinking at exactly the rate predicted by general relativity, if the system was losing energy to gravitational wave radiation. The agreement between theory and observation was so precise that Russell Hulse and Joseph Taylor were awarded the Nobel Prize in Physics in 1993 for providing the first evidence that gravitational waves exist. Yet even this triumph was indirect. The waves themselves remained undetected. The direct detection of gravitational waves required instruments of almost unimaginable sensitivity. LIGO consists of two facilities, one in Louisiana and one in Washington State, each containing an L-shaped laser interferometer with arms 4 kilometers long. Laser light bounces back and forth between mirrors at the ends of each arm, and when a gravitational wave passes through the detector, it slightly changes the lengths of the arms, causing the laser beams to go in and out of phase with each other. The engineering challenges were extraordinary. The mirrors must be isolated from all sources of vibration, from seismic waves generated by distant earthquakes to the thermal motion of atoms in the mirror surfaces themselves. The laser light must be stabilized to extraordinary precision, and the entire apparatus must be maintained in an ultra-high vacuum to prevent even air molecules from interfering with the measurements. When LIGO finally achieved the required sensitivity in 2015, the first detection came almost immediately. On September 14, 2015, at 09:50:45 UTC, both LIGO detectors simultaneously recorded a characteristic chirp signal, a rapid increase in frequency and amplitude lasting about 0.2 seconds. The signal matched the predicted waveform from two black holes, with masses about 29 and 36 times that of the Sun, merging about 1.3 billion light-years away. This detection, announced in February 2016, marked the beginning of gravitational wave astronomy. The signal, designated GW15914, confirmed Einstein's century-old prediction and opened an entirely new window on the universe. For the first time, humanity could observe cosmic events that produce no light, no heat, no electromagnetic radiation of any kind, collisions between black holes that would otherwise remain forever hidden from view. The information encoded in gravitational wave signals is remarkably rich. The early phase of the signal, when the black holes are still spiraling inward, reveals their individual masses and provides constraints on their spins. The amplitude of the waves depends on the distance to the source, while the rate at which the frequency increases reflects the dynamics of the inspiral. The final merger and ring-down phases provide information about the mass and spin of the final black hole, allowing astronomers to test general relativity's predictions about black hole dynamics. Since that first detection, LIGO and its European counterpart Virgo have observed dozens of black hole mergers, each providing new insights into these mysterious objects. The detections have revealed that black hole binaries are more common than many astronomers expected, suggesting that the universe is filled with these invisible pairs, slowly spiraling toward eventual merger. The black holes observed through gravitational waves have been surprisingly diverse. Some mergers involve black holes with nearly equal masses, while others show extreme mass ratios where a small black hole spirals into a much larger one. Some black holes appear to be spinning rapidly, while others rotate slowly or not at all. This diversity provides clues about how binary black holes form and evolve over cosmic time. One of the most remarkable aspects of gravitational wave detection is the precision with which astronomers can measure the properties of the merging black holes. Even though the events occur billions of light-years away and last only a few tenths of a second, the waves carry enough information to determine the masses of the black holes to within a few percent, and their distance to within about 20%. The waves also provide tests of general relativity in its most extreme regime. The enormous gravitational fields and high velocities involved in black hole mergers create conditions that cannot be replicated in any laboratory on Earth. Yet every observation has confirmed Einstein's predictions with remarkable accuracy, validating our understanding of gravity even in these most extreme environments. Perhaps most remarkably, gravitational waves travel through the universe almost completely unimpeded. Unlike light, which can be absorbed, scattered, or blocked by dust and gas, gravitational waves pass through matter as if it weren't there. This means that gravitational wave observatories can peer into regions of the universe that are completely opaque to conventional telescopes, observing events that occurred in the hearts of galaxies, behind dense clouds of gas and dust, or even in the very early universe when it was too hot and dense for light to travel freely. The detection of gravitational waves has also opened up the possibility of multi-messenger astronomy, where the same cosmic event is observed through both gravitational waves and electromagnetic radiation. In 2017, LIGO and Virgo detected gravitational waves from the merger of two neutron stars, an event that was also observed by gamma-ray telescopes, optical telescopes, and radio telescopes around the world. This first multi-messenger detection of a gravitational wave source provided unprecedented insights into the physics of neutron star mergers and the origin of heavy elements in the universe. Future gravitational wave detectors promise even greater sensitivity and discovery potential. The European Space Agency's planned Laser Interferometer Space Antenna, LISA, will consist of 3 spacecraft arranged in a triangular formation with side lengths of 2.5 million kilometers, making it sensitive to gravitational waves with much lower frequencies than ground-based detectors can observe. LISA will be able to detect the gravitational waves from supermassive black hole mergers, the slow in spiral of stellar mass black holes into supermassive black holes, and perhaps even the relic gravitational waves from the Big Bang itself. The waves that LIGO detects arrive at Earth as faint oscillations in spacetime, but their journey began in some of the most violent events the universe can produce. Each wave carries within it the signature of matter and energy, pushed to the absolute limits of physics, where space and time become malleable, and the distinction between matter and geometry begins to blur. To contemplate gravitational waves is to marvel at the interconnectedness of the cosmos. An event that occurs in a distant galaxy billions of years ago eventually reaches us as a subtle trembling in the fabric of reality itself. These waves connect us directly to the most extreme events in the universe, allowing us to witness cosmic catastrophes that would otherwise remain forever hidden in darkness. In the end, gravitational waves represent more than just a new tool for astronomy. They are a new way of experiencing the universe. Through these ripples in space-time, we can feel the pulse of creation itself, the rhythm of matter and energy dancing to the tune of Einstein's equations. They remind us that we live not in empty space, but in a dynamic, living geometry that carries the stories of distant worlds in its very structure. To understand the cosmic significance of black hole collisions, we must step back and view them not as isolated events, but as recurring themes in the universe's long symphony. These mergers have been occurring since the first generation of massive stars died billions of years ago, each collision adding another verse to the gravitational wave background that permeates all of space. The black holes we observe merging today are the culmination of stellar evolution that began when the universe was young, their collisions representing the final chapters in stories that started with the very first stars. In the early universe, roughly 13 billion years ago, the conditions were very different from what we observe today. The first stars were massive giants, perhaps hundreds of times more massive than our Sun, burning through their nuclear fuel in just a few million years before collapsing into black holes. These primordial black holes were likely more massive than most of the stellar black holes we see today, and they formed in a universe that was smaller, denser, and more conducive to the close encounters that lead to binary systems. The formation of binary black holes in the early universe may have followed different pathways than those we see in the modern cosmos. In dense stellar clusters, black holes could have formed binaries through gravitational capture, where two initially unbound black holes lost energy through close encounters with other stars until they became gravitationally bound to each other. In some cases, three-body interactions may have ejected one black hole from a cluster while leaving behind a tightly bound binary pair. Another formation channel involves the common envelope phase of binary stellar evolution. When one star in a binary system evolves into a red giant, its expanded outer layers can engulf its companion star. The companion then spirals inward through the giant's envelope, friction causing both stars to lose orbital energy, while the envelope is ejected into space. This process can bring the stellar cores close enough that they remain bound even after both stars have collapsed into black holes. The metallicity of the early universe, its abundance of elements heavier than hydrogen and helium, was much lower than it is today. This difference profoundly affected stellar evolution and the formation of black holes. Low metallicity stars lose less mass through stellar winds during their lifetimes, allowing them to retain more mass when they finally collapse. This means that the first generation of black holes was likely more massive on average than those forming today. As the universe evolved and successive generations of stars enriched the interstellar medium with heavy elements, the characteristics of black hole formation gradually changed. Stars in metal-rich environments lose more mass through stellar winds, producing smaller black holes when they collapse. They are also more likely to experience pair instability supernovae, explosive events that completely destroy the star and leave no black hole remnant behind. The merger rate of black hole binaries has varied dramatically over cosmic time. In the early universe, when star formation rates were higher and galaxies were smaller and denser, the conditions were more favorable for binary black hole formation. As the universe expanded and galaxies grew larger, the typical separations between stars increased, making binary formation less common. However, the time delay between binary formation and merger means that we are still observing the consequences of processes that occurred billions of years ago. A binary black hole system formed in the early universe might take many billions of years to spiral together and merge, meaning that some of the mergers we detect today originated from stellar evolution that occurred when the universe was less than half its current age. The study of gravitational wave detections has begun to reveal the demographics of black hole mergers across cosmic history. The masses of merging black holes observed by LIGO and Virgo show a characteristic distribution, with most systems involving black holes in the range of 10 to 50 solar masses. This mass distribution encodes information about the stellar evolution processes that created these black holes and the environments in which they formed. Some of the detected mergers involve black holes with masses that challenge our understanding of stellar evolution. The merger GW190521, detected in 2019, involved black holes with masses of approximately 85 and 66 solar masses, creating a final black hole of about 142 solar masses. Black holes in this mass range are difficult to explain through conventional stellar evolution, as stars massive enough to produce them should undergo pair instability supernovae that leave no black hole behind. This observation suggests that some black holes may form through alternative pathways, such as hierarchical mergers, where the products of previous black hole collisions serve as the progenitors for subsequent mergers. In dense stellar environments, a black hole formed from a previous merger might acquire a new companion and eventually merge again, building up mass through multiple generations of collisions. The detection of gravitational waves has also revealed that black hole spins in merging systems are generally lower than theoretical models predicted. While some black holes appear to be spinning rapidly, many show little or no rotation. This distribution of spins provides clues about the formation mechanisms of binary black holes and the processes that determine their angular momentum. As we look toward the future, the merger rate of black hole binaries is expected to evolve in response to the changing conditions in the universe. Star formation rates have been declining for several billion years as the universe expands and the density of gas available for star formation decreases. This trend will eventually lead to a decline in the formation rate of new binary black holes, though the mergers we observe today will continue for many billions of years as existing systems complete their death spirals. The cosmic merger rate also depends on the metallicity evolution of the universe. As successive generations of stars continue to enrich the interstellar medium with heavy elements, the conditions for black hole formation will continue to change. Future mergers may involve smaller black holes on average, as metal-rich stellar evolution produces less massive remnants. Looking back across cosmic time, each gravitational wave detection represents not just a single collision, but the endpoint of a complex evolutionary process that spans billions of years. The waves carry within them the signatures of stellar nucleosynthesis, binary evolution, dynamical interactions in stellar clusters, and the gradual orbital decay driven by gravitational radiation. They are, in a very real sense, fossils of cosmic history, preserving information about conditions in the early universe and the processes that shaped the first stars and galaxies. The population of binary black holes that we observe today is the cumulative result of 13 billion years of stellar evolution, merger, and accretion. Some systems may have formed recently in the local universe, while others began their journey toward collision when the first galaxies were still taking shape. The gravitational waves from their mergers arrive at Earth as messengers from across cosmic time, each signal carrying news of events that occurred at different epochs in the universe's history. This historical perspective reveals black hole mergers to be not random catastrophes, but natural consequences of the universe's evolution. They represent the inevitable endpoints of stellar evolution, the recycling of matter and energy that has been ongoing since the first stars began to shine. In their collisions, black holes participate in the same cosmic cycles that govern the formation of galaxies, the chemical evolution of the universe, and the eventual fate of all matter and energy. The story of black hole mergers throughout history is still being written, both in the ongoing collisions that continue to occur throughout the universe and in the gravitational wave signals that are still travelling toward us from distant cosmic catastrophes. Each new detection adds another chapter to this epic tale, revealing new details about the population of black holes, the physics of their interactions, and the role they play in shaping the cosmos. As our gravitational wave detectors become more sensitive, and we begin to observe mergers at greater distances, we will peer ever deeper into cosmic history, eventually observing black hole collisions that occurred when the universe was young and the first generation of stars was just beginning to die. These ancient signals will carry information about the very earliest epochs of cosmic evolution, providing insights into the formation of the first black holes and the conditions that prevailed in the primordial universe. When two black holes collide billions of light years away, the event seems impossibly remote from our daily lives. Yet the gravitational waves produced by such mergers carry their influence across the cosmos, eventually passing through our bodies, our planet, and our entire solar system as they continue their journey to the edge of the observable universe. In a very real sense, every black hole collision touches everything in existence, linking the most violent events in the cosmos to the most mundane objects on Earth through the invisible threads of curved space-time. The passage of a gravitational wave is unlike anything else in physics. As the wave travels through space at the speed of light, it alternately stretches and compresses distances in directions perpendicular to its path of travel. When a wave passes through Earth, it briefly changes the distance between every pair of objects on the planet. Buildings become slightly taller, then slightly shorter. The separation between cities fluctuates by amounts smaller than atomic nuclei. Even the bonds between atoms experience tiny oscillating stresses as space-time itself flexes around them. These effects are utterly imperceptible to human senses. The strongest gravitational waves ever detected change distances by amounts roughly 10,000 times smaller than the width of a proton. To put this in perspective, if you were to stretch the distance from Earth to the nearest star by the width of a human hair, the proportional change would still be millions of times larger than what gravitational waves do to local distances. Yet despite their incredible subtlety, these waves carry enormous amounts of information about some of the most extreme events in the universe. The wave that LIGO detected on September 14, 2015, had travelled for 1.3 billion years before reaching Earth. During its journey, it passed through countless galaxies, star systems, planets, and clouds of interstellar gas and dust. Unlike light, which can be absorbed, scattered, or blocked by matter in its path, the gravitational wave encountered virtually no obstacles. It arrived at Earth carrying essentially the same information it had when it left the collision site, providing an unobstructed view of an event that occurred when complex life on Earth consisted of nothing more than simple single-celled organisms. The detection process itself is a marvel of precision engineering and quantum physics. The LIGO detectors must isolate their test masses from every conceivable source of vibration, while remaining sensitive to the minute distortions caused by passing gravitational waves. This requires suspending multi-kilogram mirrors from elaborate pendulum systems that filter out seismic vibrations, while simultaneously using feedback systems to counteract other sources of noise. Even the quantum nature of light itself becomes a limitation. The laser light used to measure distance, changes in the detector arms, is subject to quantum uncertainty, creating random fluctuations that can mask weak gravitational wave signals. At the most sensitive frequencies, LIGO operates at the boundary where quantum effects begin to limit the precision of measurements, requiring sophisticated techniques to reduce quantum noise. When a gravitational wave passes through the detector, it creates a characteristic signature in the laser light. The wave's effect on space-time causes the lengths of the detector arms to oscillate, which in turn causes the laser beams travelling along those arms to go in and out of phase with each other. This phase shift is measured using laser interferometry, the same basic technique used in many precision measurement devices, but pushed to extraordinary extremes of sensitivity. The data analysis required to extract gravitational wave signals from the detector noise is almost as challenging as the detection itself. The raw data from LIGO contains signals from countless sources: seismic activity, thermal fluctuations, electromagnetic interference, and even the occasional glitch from unknown causes. Finding the faint signature of a gravitational wave in this noisy environment requires sophisticated algorithms that can recognize the characteristic patterns produced by different types of astrophysical sources. The technique relies heavily on matched filtering, a process that compares the observed data to theoretical templates of expected gravitational wave signals. These templates are generated using numerical simulations of black hole mergers, neutron star collisions, and other astrophysical phenomena. When the data matches a template with high statistical significance, it indicates the presence of a gravitational wave signal. The ripple effect extends far beyond the immediate detection. Each gravitational wave discovery provides new insights into fundamental physics, astrophysics, and cosmology. The waves carry information about the masses, spins, and orbital dynamics of the merging objects, allowing astronomers to study black holes and neutron stars in ways that would be impossible through electromagnetic observations alone. Gravitational wave astronomy has already revealed surprising aspects of the black hole population. Before LIGO began operations, astronomers knew of only about 20 stellar mass black holes in our galaxy, all identified through their gravitational effects on visible companion stars. In just a few years of operation, gravitational wave detectors have observed dozens of black hole mergers, revealing a population of binary black holes that was largely hidden from conventional astronomy. The discoveries have also provided new tests of general relativity in its most extreme regime. The enormous gravitational fields and high velocities involved in black hole mergers create conditions that cannot be replicated in terrestrial laboratories. Each detection confirms Einstein's predictions about the behavior of spacetime under these extreme conditions, providing confidence in our understanding of gravity and opening the door to searches for physics beyond general relativity. The ripples from black hole collisions also contribute to the stochastic gravitational wave background, a faint wash of gravitational radiation that permeates all of space. This background consists of the superposition of gravitational waves from countless unresolved sources throughout the universe, creating a kind of cosmic static that future detectors may be able to measure. Like the cosmic microwave background radiation that carries information about the early universe, the gravitational wave background encodes information about the history of black hole and neutron star mergers across cosmic time. Looking toward the future, the ripple effect of gravitational wave astronomy will likely extend into many areas of science. The precise timing requirements for gravitational wave detection are driving advances in laser technology, vacuum systems, and vibration isolation. The data analysis techniques developed for gravitational wave astronomy are finding applications in other fields that must extract weak signals from noisy data. The international network of gravitational wave detectors continues to expand, with new facilities under construction in Japan and India, and proposed detectors in Australia and other locations. This global network will provide better sky localization of gravitational wave sources and enable more detailed studies of the waves themselves, including their polarization properties and potential deviations from general relativity's predictions. Space-based gravitational wave detectors represent the next frontier in this field. The proposed Laser Interferometer Space Antenna, LISA, will consist of 3 spacecraft arranged in a triangular formation, with side lengths of millions of kilometers. This enormous scale will make LISA sensitive to gravitational waves with much lower frequencies than ground-based detectors can observe, opening up new classes of sources, including supermassive black hole mergers and the in-spiral of stellar mass black holes into supermassive ones. The ripple effects of black hole collisions thus extend far beyond the immediate astrophysical consequences. They have opened an entirely new field of astronomy, provided new tests of fundamental physics, and created technologies that will benefit many areas of science and engineering. Most importantly, they have given humanity a new sense, the ability to feel the universe trembling as cosmic catastrophes unfold in the distant darkness. In a profound way, gravitational waves connect us directly to the most extreme events in the cosmos. When a gravitational wave passes through your body, you are briefly and imperceptibly distorted by the same space-time curvature that was created by colliding black holes billions of years ago and billions of light years away. The wave carries within it the signature of matter and energy pushed to the absolute limits of physics, connecting the smallest scales of human experience to the largest scales of cosmic violence through the invisible medium of curved space-time. In the brief history of gravitational wave astronomy, certain collisions have achieved celebrity status, not just for their scientific importance, but for the profound ways they have changed our understanding of the universe. These cosmic encounters, each lasting only seconds, yet encoding billions of years of evolution, have become the landmarks by which we measure our progress in detecting and understanding the most violent events in the cosmos. Like astronomical celebrities caught in the act of their most dramatic performances, these black hole pairs have given us front row seats to some of the universe's most spectacular shows. The first and perhaps most famous of these collisions goes by the prosaic designation GW5914, marking the date of its detection, September 14th. This signal represents humanity's first direct detection of gravitational waves and our first observation of a black hole merger. The system consisted of two black holes with masses approximately 29 and 36 times that of our Sun, spiraling together in their final dance before merging into a single black hole of about 62 solar masses. The missing 3 solar masses had been converted entirely into gravitational wave energy and radiated away into space, demonstrating Einstein's famous equation E_mc² on a cosmic scale. What makes GW50914 particularly remarkable is not just its historical significance, but the clarity of its signal. The gravitational waves swept upward in frequency from about 35 Hz to 350 Hz over the course of 0.2 seconds, creating the characteristic chirp that matches theoretical predictions with extraordinary precision. The signal was strong enough to be visible by eye in the raw detector data, requiring no sophisticated analysis techniques to recognize a cosmic gift to humanity's first attempt at gravitational wave astronomy. The collision occurred approximately 1.3 billion years ago in a distant galaxy, when life on Earth consisted of nothing more than simple single-celled organisms. The gravitational waves from this ancient catastrophe travelled across the cosmos for longer than complex life has existed on our planet, arriving just as human technology had finally achieved the sensitivity required to detect them. In a poetic sense, the waves and humanity reached the same moment of readiness simultaneously. Another landmark event occurred on August 14, 2017, with the detection of GW17814, which became the first gravitational wave signal observed by 3 detectors simultaneously. The European Virgo detector had recently joined the LIGO collaboration, creating a 3-detector network that could pinpoint the location of gravitational wave sources much more precisely than 2 detectors alone. This triangulation capability marked a crucial step toward multi-messenger astronomy, where gravitational wave detections can be coordinated with observations by conventional telescopes. The masses involved in GW1704 were somewhat smaller than the first detection, about 25 and 31 solar masses, but the 3-detector observation provided unprecedented insights into the properties of gravitational waves themselves. For the first time, astronomers could measure the polarization of gravitational waves and confirm that they propagate at the speed of light, exactly as Einstein's theory predicts. Perhaps the most scientifically revolutionary detection came just 3 days after GW17814, with the observation of GW17817, the first gravitational wave signal from merging neutron stars. While not a black hole collision, this detection proved that gravitational wave astronomy could observe a much broader range of cosmic phenomena than initially expected. The neutron-star merger was also observed by gamma-ray satellites and optical telescopes around the world, creating the first multi-messenger observation of a gravitational wave source and opening an entirely new era of astronomy. Returning to black hole mergers, one of the most puzzling detections came in 2019 with GW 1900521, an event that challenged astronomers' understanding of how massive black holes form. The collision involved black holes with masses of approximately 85 and 66 solar masses, creating a final black hole of about 142 solar masses. What made this detection extraordinary was that black holes in this mass range are extremely difficult to explain through conventional stellar evolution. Stars massive enough to produce black holes in the 80-90 solar mass range should undergo pair instability supernovae, explosive events that completely destroy the star and leave no black hole remnant behind. The detection of GW 1900521 suggested that some black holes might form through alternative pathways, such as hierarchical mergers, where the products of previous black hole collisions serve as the seeds for subsequent mergers. The signal from GW 19521 was also unusual in other ways. It was much shorter than typical black hole merger signals, lasting only about 0.1 seconds and containing only a few orbital cycles before merger. This brevity made it more difficult to extract detailed information about the individual black holes, but it provided insights into mergers involving the most massive black holes yet observed through gravitational waves. Another remarkable detection, GW 190412, revealed the first clear observation of a black hole merger with significantly unequal masses. One black hole weighed about 30 solar masses, while its companion was only about 8 solar masses, creating a system where the mass ratio was nearly 4. This asymmetry produced distinctive features in the gravitational wave signal, including higher order modes that had never been clearly observed before. The unequal masses of GW 190412 also caused the orbital plane to precess, to wobble like a spinning top, as the black holes spiraled together. This precession left its signature in the gravitational waves, allowing astronomers to measure the orientations and spins of the black holes with greater precision than in more symmetric systems. Each of these famous collisions has contributed unique insights to our understanding of black holes and fundamental physics. GW 150914 proved that gravitational waves exist and that black hole mergers occur in nature. GW 150814 demonstrated the power of multi-detector observations and confirmed the properties of gravitational waves themselves. GW 15021 revealed the existence of black holes in unexpected mass ranges and suggested new formation mechanisms. GW 1502 showed how asymmetric mergers can provide detailed information about black hole properties. Collectively, these detections have revealed a universe far richer in black hole mergers than many astronomers expected. The observed merger rate suggests that binary black hole systems are relatively common, with a new merger occurring somewhere in the observable universe roughly once every few minutes. This high rate indicates that the universe has been producing binary black holes efficiently throughout cosmic history, either through stellar evolution or through dynamical processes in dense stellar environments. The diversity of the observed systems has also been surprising. Black hole masses range from about 5 solar masses to over 80 solar masses, with a distribution that encodes information about stellar evolution, supernova physics, and binary formation mechanisms. Some black holes appear to be spinning rapidly, while others show little rotation, providing clues about their formation histories and the processes that determine their angular momentum. The precision with which astronomers can measure the properties of merging black holes continues to improve with each detection. Modern analyses can determine black hole masses to within a few percent, and provide meaningful constraints on their spins and the geometry of their orbits. This precision rivals or exceeds what can be achieved through electromagnetic observations of black holes in our own galaxy. Looking toward the future, the population of famous black hole collisions will undoubtedly continue to grow. As detector sensitivity improves and new facilities come online, Astronomers expect to observe hundreds or even thousands of black hole mergers per year. Some of these will likely involve even more massive black holes, asymmetric mass ratios, or exotic spin configurations that will further test our understanding of black hole physics. The most eagerly anticipated future detections include the first observations of intermediate mass black holes, objects with masses between stellar black holes and supermassive black holes that have proven elusive to conventional astronomy. Space-based detectors like LISA will eventually observe the mergers of supermassive black holes, events so energetic they will be detectable across the entire observable universe. Each famous collision represents not just a scientific discovery, but a cosmic milestone in humanity's quest to understand the universe. These black hole pairs, locked in gravitational embraces that began millions of years ago, have become our teachers, revealing the secrets of gravity, space-time, and the most extreme physics in nature. Their celebrity status is well deserved. They are the first ambassadors from a previously hidden universe of dark, colliding objects that have been shaping the cosmos since the first stars began to die. In their brief moments of visibility, lasting only seconds but carrying information gathered over billions of years, these famous collisions remind us that we live in a universe far stranger and more dynamic than previous generations could have imagined. They are cosmic celebrities, not because of their glamour, but because of their willingness to reveal, in the language of rippling spacetime, the most profound secrets of existence itself. In the seconds following a black hole collision, as the gravitational wave signal fades to silence, and the newly merged black hole settles into its final configuration, a profound quiet descends upon the scene. The most violent event the universe can produce has concluded, leaving behind a single, more massive black hole that will likely remain undisturbed for billions of years. This aftermath is not dramatic in the way human minds expect from cosmic catastrophes. There are no glowing debris fields, no shockwaves racing outward, no spectacular light shows. Instead, there is simply a new arrangement of space-time geometry, a slightly different curvature in the fabric of reality, and the gradual return of cosmic tranquility. The merged black hole that emerges from the collision carries within its event horizon the entire history of its formation. Its mass represents the sum of its progenitors, minus the energy radiated away as gravitational waves. Its spin encodes information about the orbital angular momentum of the merging system, and the individual rotations of the original black holes. Its final state, determined by the no-hair theorem of general relativity, depends only on these two quantities, mass and angular momentum, with all other details of the collision eventually forgotten as the black hole settles into equilibrium. This settling process, known as the ring-down phase, produces the final gravitational waves emitted by the system, like a struck bell that rings with characteristic tones as it returns to silence. The newly formed black hole oscillates in specific modes determined by its mass and spin. These oscillations gradually decay as energy is radiated away, leaving behind a perfectly smooth, stationary black hole described by the elegant mathematics of the Kerr solution. The environment around the merged black hole depends largely on what was present before the collision occurred. In many cases, the black holes merged in the sparse regions between galaxies, where matter is scarce and the surrounding space is nearly empty. Here, the aftermath is truly quiet, a massive but invisible object sitting alone in the cosmic void, detectable only through its gravitational influence on passing light, or the occasional particle that wanders too close to its event horizon. In other cases, the collision may have occurred within a galaxy, perhaps in a globular cluster, or in the dense central regions where supermassive black holes reside. Here, the newly formed black hole inherits whatever environment surrounded the original pair: gas clouds, nearby stars, or the accretion disks that may have been feeding one or both of the progenitor black holes. The merger process itself can disrupt these environments, flinging matter outward and temporarily clearing the space around the new black hole. If significant amounts of matter are present, the aftermath can be more dramatic, though still subtle compared to the collision itself. Gas that was previously in stable orbits around one of the black holes may find itself on chaotic trajectories around the merged object. Some of this material may be ejected entirely, while other portions settle into a new accretion disk around the final black hole. As this matter spirals inward, it heats up and begins to glow, potentially making the merged black hole visible to conventional telescopes for the first time. The feeding of the merged black hole can trigger what astronomers call a quasar, or active galactic nucleus, where the infalling matter creates brilliant jets and disk emissions that can outshine entire galaxies. However, this feeding phase is temporary. Once the disturbed matter has either fallen into the black hole or been ejected from the system, the black hole returns to its quiet state, invisible except for its gravitational effects. The space around the merged black hole also carries subtle imprints of the collision. The gravitational waves that propagated outward during the merger may have slightly disturbed nearby matter, creating density fluctuations that could influence future star formation or the dynamics of stellar orbits. These effects are incredibly weak, but they represent the black hole collision's contribution to the ongoing evolution of its cosmic neighborhood. For any hypothetical observers in the vicinity, though they would need to be at safe distances of many light years, the collision would have been completely invisible to the naked eye. Black holes emit no light, and the gravitational waves they produce are imperceptible to human senses. The only sign of the cosmic catastrophe would have been the subtle gravitational perturbations that might have slightly altered the orbits of planets around nearby stars, or created minute tidal effects in any large bodies of matter. The newly formed black hole begins its existence in a state of perfect isolation. Unlike stars which shine and heat their surroundings, or planets which can be observed through reflected light, the merged black hole interacts with its environment only through gravity. It sits at the center of its own private universe, bounded by an event horizon that ensures its interior remains forever hidden from outside observers. This isolation is both profound and permanent. The black hole will continue to exist long after the stars around it have exhausted their fuel and died, long after galaxies have merged and star formation has ceased throughout the universe. It represents one of the most enduring forms of matter in the cosmos, a concentration of mass energy that will persist until quantum effects cause it to slowly evaporate through Hawking radiation, a process that for stellar mass black holes takes far longer than the current age of the universe. In the immediate aftermath of merger, the black hole retains the orbital motion that the binary system possessed before collision. This means the merged black hole may be moving through its galaxy or cluster at speeds of hundreds of kilometers per second, a so-called kicked black hole that received a recoil velocity from the asymmetric emission of gravitational waves during merger. These kicked black holes can travel vast distances, sometimes even escaping their parent galaxies entirely to wander through intergalactic space. The phenomenon of black hole kicks is particularly important for understanding the demographics of black holes throughout the universe. Strong kicks can remove merged black holes from the dense environments where they formed, reducing the likelihood of subsequent mergers and affecting the growth of supermassive black holes at galactic centers. The strength of the kick depends on the masses and spins of the merging black holes and the geometry of their final orbital configuration. For supermassive black hole mergers, which occur when entire galaxies collide and merge, the aftermath can have more noticeable effects on the surrounding environment. These mergers can disrupt the orbits of stars near galactic centers, creating stellar streams and affecting the overall structure of galactic nuclei. The gravitational waves from such events are so powerful they can influence the evolution of matter over vast regions of space. The quiet aftermath of black hole collisions also represents a fundamental transformation in the information content of the universe. According to our current understanding of black hole physics, the detailed information about the internal structure of the merged black holes is lost forever, hidden behind event horizons that prevent any information from escaping. This creates what physicists call the black hole information paradox, a conflict between general relativity and quantum mechanics about whether information can be permanently destroyed. Some theories suggest that information is preserved in subtle correlations between Hawking radiation emitted over the black hole's lifetime, but these ideas remain highly speculative. The merger represents a moment when vast amounts of information about stellar evolution, nuclear physics, and cosmic history disappear from the observable universe, preserved only in the gross properties of mass and angular momentum that characterize the final black hole. The aftermath also marks the end of one evolutionary pathway and the beginning of another. The stellar mass black holes that merged may have been the endpoints of massive star evolution, representing the final collapse of nuclear furnaces that once powered life-sustaining energy throughout their stellar neighborhoods. Their merger creates a new entity that will follow a different evolutionary track, slowly accreting matter and growing over cosmic timescales, or in the far future, gradually evaporating through quantum processes. In the broader cosmic context, each black hole merger contributes to the gradual consolidation of matter into ever larger, more massive objects. Over billions of years, smaller black holes merge to form larger ones, which in turn may merge with others in a hierarchical process that builds up the supermassive black holes found at the centers of galaxies. The quiet aftermath of today's mergers represents a step in this long-term evolution of cosmic structure. The detection of gravitational waves from black hole mergers has also created a new kind of aftermath here on Earth, the beginning of gravitational wave astronomy as a mature observational science. Each detection adds to our census of black holes, tests general relativity in its most extreme regime, and provides insights into stellar evolution, galaxy formation, and fundamental physics. The quiet aftermath of distant collisions has become the beginning of profound new understanding about the universe we inhabit. Perhaps most remarkably, the aftermath of black hole collisions demonstrates the universe's capacity for renewal and transformation. What appears to be an ending, the violent collision of two compact objects, is revealed to be a new beginning. The merged black hole carries forward the legacy of the stellar evolution that created its progenitors, preserving their mass while discarding the details of their formation. It represents both continuity and change, destruction and creation, on the grandest scales nature can achieve. In the vast silence that follows each collision, as gravitational waves race outward at light speed and the merged black hole settles into its eternal configuration, the universe adds another chapter to its ongoing story of matter organizing itself into increasingly complex and beautiful forms. The aftermath may be quiet, but it is pregnant with possibilities, new gravitational influences that will shape nearby matter, new tests of physics that will challenge our understanding, and new questions about the nature of space, time, and existence itself. At the hearts of galaxies across the universe lurk monsters of unimaginable scale, supermassive black holes with masses millions or billions of times greater than our Sun. These giants dwarf their stellar mass cousins in every conceivable way, possessing event horizons that could encompass entire solar systems and gravitational influences that extend across thousands of light years. When supermassive black holes collide, they produce gravitational wave signals so powerful they can be detected across the entire observable universe, creating cosmic events that reshape not just the fabric of space-time, but the very galaxies that host them. The existence of supermassive black holes was once purely theoretical, inferred from the motion of stars and gas in galactic centers, and the brilliant emissions from quasars in the distant universe. Today we know that virtually every large galaxy contains a supermassive black hole at its center, and the mass of this central giant is closely correlated with properties of the galaxy itself, its central stellar bulge, its total mass, and even the velocities of stars far from the galactic core. This correlation suggests a deep connection between supermassive black holes and galaxy evolution, with each influencing the growth and development of the other over cosmic time. The black holes regulate star formation through their gravitational influence and the energy they release when feeding on surrounding matter, while the galaxies provide both the material that feeds the black holes and the gravitational environment that governs their growth. The formation of supermassive black holes remains one of the great unsolved problems in astrophysics. Unlike stellar mass black holes, which form through well understood processes of stellar collapse, supermassive black holes seem to have achieved their enormous masses too quickly in the early universe for gradual accretion to be the sole explanation. Some may have formed directly from the collapse of massive gas clouds in the primordial universe, while others might have grown from intermediate mass seed black holes through rapid accretion or mergers with other black holes. When galaxies collide and merge, a process that occurs regularly throughout cosmic history, their central supermassive black holes are eventually brought together in a gravitational dance that dwarfs even the most energetic stellar mass black hole mergers. The in-spiral phase can last for millions of years as the black holes orbit each other at distances of light years, gradually spiraling inward as they lose energy to gravitational wave radiation. Unlike stellar mass black holes, which are typically isolated objects moving through sparse interstellar space, supermassive black holes are surrounded by dense stellar environments and often by accretion disks of hot, glowing matter. When two such systems approach each other, the gravitational disruption can trigger spectacular displays as matter is funneled toward the black holes at increased rates, potentially lighting up both objects as brilliant quasars or active galactic nuclei. The final merger of supermassive black holes represents one of the most energetic events possible in the universe. The collision can convert several solar masses worth of material directly into gravitational wave energy, releasing this enormous power over the course of minutes or hours, rather than the milliseconds typical of stellar mass mergers. The gravitational waves produced are so powerful they can be detected by space-based interferometers from distances spanning the entire observable universe. However, the detection of supermassive black hole mergers requires different technology than the ground-based detectors that have revolutionized stellar mass black hole astronomy. The gravitational waves from these giants have much lower frequencies, corresponding to the much longer orbital periods and larger physical scales involved. Ground-based detectors like LIGO are sensitive to waves with frequencies of tens to thousands of hertz, while supermassive black hole mergers produce waves with frequencies of millihertz or less. The planned Laser Interferometer Space Antenna, LISA, consisting of 3 spacecraft arranged in a triangular formation with side lengths of millions of kilometers, will be sensitive to these low-frequency gravitational waves. LISA will be able to observe supermassive black hole mergers out to enormous distances, potentially detecting every such collision that occurs in the observable universe above a certain mass threshold. The scientific potential of supermassive black hole merger detection is extraordinary. These events will provide direct measurements of black hole masses and spins across cosmic time, revealing how these giants grew and evolved as the universe aged. They will also provide precise tests of general relativity in the strong field regime, where the gravitational fields are so intense they approach the theoretical limits, where quantum effects might become important. The gravitational wave signals from supermassive black hole mergers will also carry information about the cosmic expansion history, as the observed frequency and amplitude of the waves depend on the distance to the source and the expansion rate of the universe. This will make supermassive black hole mergers powerful cosmological probes, potentially providing new insights into dark energy and the ultimate fate of the universe. The environmental effects of supermassive black hole mergers extend far beyond the immediate vicinity of the collision. The gravitational waves can disrupt the orbits of stars throughout the galactic center, creating complex dynamical structures and potentially ejecting some stars from the galaxy entirely. The merged black hole may also receive a kick velocity from asymmetric gravitational wave emission, potentially causing it to oscillate within the galactic center, or even escape the galaxy altogether. When supermassive black holes merge within gas-rich environments, the collision can trigger massive inflows of material toward the merged black hole, creating some of the most luminous objects in the universe. These post-merger active galactic nuclei can outshine their entire host galaxies and remain visible across cosmic distances for millions of years, providing electromagnetic counterparts to the gravitational wave signals. The study of supermassive black hole mergers also provides insights into the hierarchical formation of cosmic structure. As smaller galaxies merge to form larger ones, their central black holes eventually merge as well, creating a population of increasingly massive objects at the centers of increasingly massive galaxies. This process links the smallest scales of black hole physics to the largest scales of cosmic evolution. The timing of supermassive black hole mergers relative to galaxy mergers is a complex problem in theoretical astrophysics. While the galaxies themselves may merge over hundreds of millions of years, the central black holes must overcome what is known as the final parsec problem, the difficulty of losing the last bit of orbital energy required to bring them from separations of about 1 parsec, roughly 3 light-years, to actual contact. This final stage of the inspiral may require interactions with surrounding stars or gas to remove orbital energy, or it may depend on 3-body interactions involving multiple black holes in complex galactic merger scenarios. Understanding these processes is crucial for predicting the rate at which supermassive black hole mergers occur and the gravitational wave signals they produce. The role of supermassive black holes in cosmic evolution extends beyond their individual mergers. As the most massive objects in the universe, apart from galaxy clusters themselves, they serve as anchors around which galactic structure forms and evolves. Their gravitational influence shapes the distribution of matter throughout their host galaxies, while their occasional feeding episodes can regulate star formation and affect the chemical evolution of galactic gas. The detection of gravitational waves from supermassive black hole mergers will mark the beginning of a new era in both gravitational wave astronomy and galaxy evolution studies. Unlike stellar mass black holes, which are difficult to observe through conventional means, supermassive black holes are already well studied through their electromagnetic emissions and gravitational effects on surrounding matter. Gravitational wave observations will add a completely new dimension to this knowledge, revealing the dynamics of the mergers themselves and providing unprecedented tests of general relativity. The anticipated merger rate for supermassive black holes is much lower than for stellar mass systems, perhaps 1 detection per year for the most sensitive future detectors. However, each detection will be extraordinarily rich in scientific content, providing months or even years of advance warning as the black holes spiral together and allowing for coordinated observations across the electromagnetic spectrum. In the grand hierarchy of cosmic structures, supermassive black hole mergers represent the collision of the universe's most extreme individual objects. They are the ultimate expression of gravity's power to concentrate matter and energy, and their collisions produce the strongest gravitational waves nature can generate. When LISA and other space-based detectors begin operations in the coming decades, they will open a new window on these cosmic leviathans, revealing their hidden dynamics and their central role in shaping the universe we observe today. Between the well-understood stellar mass black holes born from collapsing stars and the supermassive giants that anchor galaxies lies a mysterious population that has long puzzled astronomers: intermediate mass black holes. These objects, with masses between roughly 100 and 100,000 times that of the Sun, occupy a crucial but poorly understood rung on the cosmic ladder of black hole formation and evolution. Their collisions, when they occur, may hold keys to understanding how the first supermassive black holes formed in the early universe, and how matter organizes itself into the most extreme structures nature can create. The mystery of intermediate mass black holes begins with their apparent scarcity. While stellar mass black holes are relatively common products of stellar evolution, and supermassive black holes appear to inhabit virtually every large galaxy, intermediate mass black holes have proven remarkably elusive. This scarcity is puzzling, because theoretical models suggest they should form naturally through several different pathways, yet firm observational evidence for their existence remains limited. One potential formation mechanism involves the collapse of very massive stars that existed in the early universe, when the lack of heavy elements allowed stars to grow much larger than those forming today. These population 3 stars might have reached masses of hundreds or even thousands of solar masses before collapsing directly into intermediate mass black holes. However, no such stars exist in the modern universe, making this formation channel purely historical. Another possibility is that intermediate mass black holes form through the runaway collision of stars in dense stellar clusters. In the cores of globular clusters, where millions of stars are packed into regions only a few light years across, stellar collisions can occasionally occur. If a particularly massive star forms through such collisions and then undergoes core collapse, it might produce an intermediate mass black hole that subsequently grows through accretion or further mergers. Dynamical processes in stellar clusters can also concentrate stellar mass black holes toward the cluster center, where they might merge repeatedly in a hierarchical process. Each merger produces a slightly more massive black hole, and over many generations, these objects could grow into the intermediate mass range. This scenario predicts that intermediate mass black holes should preferentially form in the densest stellar environments, where encounter rates are highest. The detection challenges for intermediate mass black holes are formidable. Unlike supermassive black holes, which often reveal themselves through their gravitational effects on surrounding matter, or through the brilliant emissions from their accretion disks, intermediate mass black holes are typically too small to significantly influence their galactic environments, and too isolated to maintain substantial accretion flows. Some candidate intermediate mass black holes have been identified through their gravitational effects on nearby stars, or through X-ray emissions from accretion. However, many of these candidates remain disputed, with alternative explanations involving multiple stellar mass black holes or unusual stellar populations. The lack of definitive identifications has made intermediate mass black holes one of the most sought-after populations in modern astronomy. Gravitational wave astronomy offers new hope for resolving the intermediate mass black hole mystery. When these objects merge with each other, or with stellar mass black holes, they produce gravitational wave signals that are distinct from both stellar mass and supermassive mergers. The frequencies involved are intermediate between the high frequencies characteristic of stellar mass mergers and the millihertz waves produced by supermassive black hole collisions. Current gravitational wave detectors are most sensitive to mergers involving objects in the intermediate mass range, particularly when one component has a mass between 100 and 1,000 solar masses. Such mergers would produce strong signals lasting tens of seconds to several minutes, providing detailed information about the masses, spins, and orbital dynamics of the merging objects. The merger GW19521, detected in 2019, may represent the first observation of intermediate mass black hole formation through gravitational wave astronomy. The collision involved stellar mass black holes with masses of approximately 85 and 66 solar masses, producing a final black hole of about 142 solar masses, firmly in the intermediate mass range. This detection demonstrated that hierarchical mergers can indeed build up black hole masses through successive collisions. However, GW190521 also raised new puzzles. The component masses were difficult to explain through conventional stellar evolution. As stars massive enough to produce 80 to 90 solar mass black holes should undergo pair instability supernovae that leave no remnant behind. This suggests that the progenitor black holes may themselves have been products of earlier mergers, indicating a complex history of hierarchical growth. The gravitational wave signal from GW19521 was also unusually short, containing only a few orbital cycles before merger. This brevity made it challenging to extract detailed information about the properties of the merging black holes, but it provided a template for identifying similar events in future observations. The detection suggested that intermediate mass black hole formation through mergers might be more common than previously expected. Future gravitational wave observations may reveal an entire population of intermediate mass black holes that has remained hidden from electromagnetic surveys. These objects might exist in isolation between galaxies, in the outer regions of galactic halos, or in environments where they produce too little electromagnetic emission to be easily detected. Gravitational waves provide a way to observe these dark objects directly through their most violent interactions. The scientific implications of intermediate mass black hole discoveries extend far beyond black hole physics itself. These objects may represent the seeds from which supermassive black holes grew in the early universe. If intermediate mass black holes formed through early stellar evolution or primordial collapse, they could have provided the starting points for rapid accretion that produced billion solar mass black holes within the first billion years of cosmic history. The distribution and properties of intermediate mass black holes also constrain models of structure formation in the early universe. The number of such objects depends on the efficiency of star formation, the typical masses of early stars, and the dynamics of stellar clusters in the first galaxies. Observations of intermediate mass black hole mergers thus provide indirect probes of conditions in the early universe that are difficult to study through other means. The merger dynamics of intermediate mass black hole systems are particularly complex because these objects exist at the boundary between different physical regimes. They are massive enough that post-Newtonian approximations begin to break down, requiring full numerical relativity calculations to predict their gravitational wave signals accurately. Yet they are not so massive that the surrounding environment significantly affects their dynamics, making them ideal laboratories for testing general relativity in isolation. When intermediate mass black holes merge with stellar mass companions, they create systems with extreme mass ratios that produce distinctive gravitational wave signatures. These extreme mass ratio in spirals involve a stellar mass black hole spiraling into a much more massive companion over thousands of orbital cycles, creating signals that can last for hours or days and provide exquisite tests of general relativity's predictions. The environmental effects of intermediate mass black hole mergers depend strongly on where they occur. Mergers in dense stellar clusters can eject the merged black hole from the cluster entirely, while mergers in galactic environments might trigger interactions with surrounding gas or dark matter. The recoil velocities from these mergers can be substantial, potentially flinging the merged object out of its host galaxy and into intergalactic space. The study of intermediate mass black holes also bridges the gap between stellar astrophysics and galaxy evolution. While stellar mass black holes are primarily products of individual stellar evolution and supermassive black holes are shaped by galactic processes, intermediate mass black holes may be influenced by both scales. Their formation and evolution provide insights into how matter organizes itself across the vast range of scales that connect stars to galaxies. As gravitational wave astronomy continues to mature, the search for intermediate mass black holes will likely become one of its primary scientific goals. These mysterious objects hold clues to some of the deepest questions in astrophysics. How did the first supermassive black holes form? What determines the efficiency of star formation in extreme environments? How do black holes grow and merge across cosmic time? The collisions of intermediate mass black holes, when they are finally observed in large numbers, may prove to be among the most scientifically valuable detections in gravitational wave astronomy. They will test our understanding of black hole formation, provide new insights into stellar evolution in extreme environments, and reveal the hidden population of dark objects that may dominate the mass budget of the universe between stars and galaxies. In the quiet spaces between the familiar populations of stellar mass and supermassive black holes, intermediate mass objects may be waiting to reveal some of the universe's best-kept secrets. Their collisions, producing gravitational waves that carry information across cosmic distances and cosmic time, will ultimately help us understand how the universe builds its most extreme structures and how matter and energy organize themselves on the grandest scales imaginable. As we look forward into the vast expanses of cosmic time, the universe promises a future filled with black hole collisions on scales and timescales that dwarf human comprehension. These future encounters will not only continue the processes we observe today, but will evolve in character as the universe itself ages, galaxies merge, and the fundamental conditions of cosmic evolution change. Some collisions are already written into the gravitational script of the cosmos, their outcomes as inevitable as the rising of tomorrow's sun, while others await the chance encounters and complex dynamics that will unfold over billions of years. The most certain of these future collisions involves the supermassive black holes at the centers of the Milky Way and Andromeda galaxies. As these two great spiral galaxies drift toward their inevitable collision, approximately 4.5 billion years from now, their central black holes, Sagittarius A/SRO in the Milky Way, weighing about 4 million solar masses, and the Andromeda galaxy's central black hole, with a mass of roughly 100 million solar masses, will eventually be brought together in a gravitational dance of unprecedented scale. The merger of these galactic titans will unfold over millions of years, beginning when the galaxies first interpenetrate and their central regions are brought within a few thousand light years of each other. The orbital decay will be driven initially by dynamical friction as the black holes interact gravitationally with surrounding stars, gradually losing energy and angular momentum until they reach separations where gravitational wave emission becomes the dominant mechanism driving their in-spiral. This future collision will produce gravitational waves so powerful they could be detected by instruments anywhere in the local group of galaxies, creating signals that persist for thousands of years as the black holes spiral from separations of light years down to final contact. The merger will convert several solar masses directly into gravitational wave energy, creating ripples in spacetime that will propagate throughout the local supercluster and beyond. But the Milky Way Andromeda collision represents just one example of countless future mergers already encoded in the current motions of galaxies throughout the universe. Every galaxy group and cluster contains multiple systems destined for eventual collision, their fates determined by the gravitational interactions that have been shaping cosmic structure for billions of years. The local group itself contains several smaller galaxies that will likely be absorbed by either the Milky Way or Andromeda before the two giants finally meet. The large and small Magellanic Clouds currently orbiting the Milky Way may spiral inward over the next few billion years, their central black holes eventually merging with Sagittarius. The Triangulum galaxy, the third largest member of the local group, faces an uncertain future that may include disruption by tidal forces or direct collision with the merged Milkdromeda system. On larger scales, the future collision rate between supermassive black holes will be determined by the ongoing merger of galaxy clusters and the hierarchical growth of cosmic structure. As dark matter halos continue to accrete smaller systems and merge with each other, the galaxies they contain will be brought together in increasingly complex gravitational interactions that eventually lead to black hole mergers. The Virgo cluster, which contains thousands of galaxies within about 50 million light-years of Earth, represents a preview of the future evolution of galactic neighborhoods. Within this dense environment, galaxy mergers occur regularly, and the central supermassive black holes of these systems will eventually coalesce into ever larger objects at the centers of the most massive cluster galaxies. However, the future of black hole collisions is not simply a continuation of present trends. As the universe continues to expand under the influence of dark energy, the accelerating expansion will gradually overcome the gravitational attraction between distant galaxy clusters. This means that future mergers will be increasingly confined to gravitationally bound structures, galaxy groups and clusters that have already decoupled from the cosmic expansion. This evolution will create a universe of cosmic islands, each centered on a massive galaxy cluster, but increasingly isolated from distant neighbors. Within these islands, black hole mergers will continue for hundreds of billions of years, but the merger rate will gradually decline as the supply of unmerged systems is exhausted and new binary formation becomes increasingly rare. The stellar mass black hole population will also evolve over cosmic time, though on somewhat different timescales. As star formation rates continue to decline throughout the universe, fewer new stellar mass black holes will be created, While existing binary systems will continue to merge over the extended timescales required for gravitational wave-driven in-spiral, some of the most interesting future collisions may involve the products of previous mergers. As hierarchical merging builds up increasingly massive black holes, some systems may undergo multiple generations of coalescence. A stellar mass black hole that merges to form an intermediate mass object might later merge again to produce an even more massive black hole, eventually growing into the supermassive range through this process of accretion and merger. The environments in which future black hole collisions occur will also evolve as the universe ages. As stars exhaust their nuclear fuel and stellar populations age, the bright gas-rich environments of active star formation will give way to quieter regions dominated by long-lived red dwarf stars and stellar remnants. This evolution will affect the observational signatures of black hole mergers, as there will be fewer opportunities for electromagnetic counterparts from disrupted gas or triggered star formation. Climate change in the cosmic environment will also influence black hole evolution through the gradual depletion of gas reservoirs. As intergalactic gas cools and falls into galaxies, and as stellar winds and supernovae expel material from galactic disks, the fuel available for black hole growth through accretion will gradually diminish. This means that future black hole growth will depend increasingly on mergers rather than gas accretion. Technological advances will revolutionize our ability to observe future black hole collisions. The planned LISA mission will be sensitive to supermassive black hole mergers throughout the observable universe, providing advance warning of these events years or even decades before they occur. This will allow for unprecedented coordination between gravitational wave and electromagnetic observations, revealing details of merger physics that are invisible to current detectors. Future detector networks may extend beyond Earth entirely, with space-based interferometers positioned throughout the solar system to create gravitational wave telescopes with baselines comparable to planetary orbits. Such instruments could achieve sensitivity levels that would detect stellar mass black hole mergers throughout the observable universe and probe the gravitational wave background created by the superposition of countless unresolved sources. The far future of black hole collisions extends into timescales that dwarf the current age of the universe. Trillions of years from now, when star formation has completely ceased and stellar populations have evolved to consist primarily of white dwarfs, neutron stars, and black holes, mergers will still continue through the slow process of gravitational wave-driven orbital decay in extremely wide binaries. In this distant future, the universe may be dominated by black holes of various masses, from stellar remnants to the supermassive giants that once anchored long-vanished galaxies. These objects will continue to merge through chance encounters and the gradual decay of bound systems, slowly concentrating the universe's remaining mass into fewer and fewer objects. Even the supermassive black holes that emerge from future galactic mergers are not permanent. Over timescales of 10^64 years or more, incomprehensibly longer than the current age of the universe, quantum effects will cause even the most massive black holes to evaporate through Hawking radiation, returning their mass energy to the vacuum through the emission of elementary particles. But long before this ultimate fate, black hole mergers will continue to eliminate the nature of gravity, spacetime, and cosmic evolution. Each future collision carries within it the history of stellar evolution, galactic dynamics, and cosmic structure formation that led to its occurrence. By observing these events, future astronomers will probe not only the physics of black holes themselves, but the entire evolutionary history of the universe that created them. The future of black hole collisions thus represents both an ending and a beginning, the final acts in the lives of individual black holes, but also the continuing evolution of cosmic structure on the grandest scales. These events will outlast stars, galaxies, and perhaps even the accelerating expansion of space itself, serving as beacons that illuminate the deepest principles governing the behavior of matter, energy, space, and time. In contemplating these future collisions, we glimpse the universe's extraordinary capacity for patience and persistence. The gravitational interactions that will drive black holes together over the next billions of years are already encoded in their current motions, following trajectories determined by the mathematics of general relativity, with the inevitability of celestial clockwork. Yet each merger will also represent a moment of creation, as two separate objects unite to form something new, sending gravitational waves racing across the cosmos with news of their transformation. When we step back from the technical details of masses, spins, and gravitational wave frequencies, black hole collisions reveal themselves as something far more profound than mere astrophysical events. They are cosmic punctuation marks in the ongoing sentence of creation, moments when the universe pauses to demonstrate the most extreme possibilities inherent in the laws of physics. These collisions connect the smallest scales of quantum mechanics to the largest scales of cosmic evolution, weaving together stories that span from the birth of the first stars to the ultimate fate of matter itself. In the grand narrative of cosmic evolution, black hole collisions represent both endings and beginnings. They mark the final chapters in the lives of the most massive stars that ever existed, the culmination of nuclear processes that forged heavy elements and powered stellar evolution for millions or billions of years. Yet they also represent new beginnings, the birth of more massive black holes that will shape the gravitational environment of their cosmic neighborhoods for eons to come. The formation of black holes traces back to the very earliest epochs of cosmic history, when the first generation of stars began to shine in a universe that contained only hydrogen, helium, and trace amounts of lithium forged in the Big Bang. These primordial giants, perhaps hundreds of times more massive than our Sun, lived brief but spectacular lives before collapsing into the first black holes. Some of those ancient objects may still exist today, having grown through mergers and accretion into the supermassive black holes we observe at galactic centers. This connection between past and future imbues black hole collisions with a sense of cosmic continuity. When two black holes merge today, they are uniting objects whose histories stretch back billions of years, whose progenitor stars witnessed the formation of the first galaxies and the beginning of chemical evolution throughout the universe. The gravitational waves from their collision carry information encoded over these vast timescales, creating signals that connect us directly to the universe's youth. The universality of gravitational physics means that black hole collisions provide a unique window into fundamental principles that operate throughout the cosmos. Unlike electromagnetic phenomena, which depend on the specific properties of matter and can be influenced by temperature, density, and chemical composition, gravitational interactions depend only on mass and energy. This makes gravitational wave astronomy a pure probe of spacetime physics, uncontaminated by the complex chemistry and thermodynamics that complicate other astronomical observations. Through black hole mergers, we can study general relativity in regimes where gravitational fields approach their theoretical limits, and matter moves at significant fractions of light speed. These observations test Einstein's century-old theory in conditions that cannot be replicated in any earthly laboratory, providing confidence in our understanding of gravity while simultaneously searching for deviations that might point toward new physics. The cosmic perspective also reveals how black hole collisions participate in the grand recycling program that governs all matter and energy in the universe. Stars forge heavy elements through nuclear fusion. Supernovae scatter these elements into space, and new generations of stars incorporate this enriched material into their cores. Black holes represent a different kind of recycling, the conversion of matter into pure gravitational energy that propagates across the cosmos as ripples in space-time itself. This recycling extends beyond individual black holes to encompass entire populations of objects across cosmic time. The merger rate we observe today reflects the cumulative history of star formation, stellar evolution, and binary formation processes that occurred billions of years ago. Future merger rates will depend on the stellar evolution occurring now, creating a connection between present processes and far future observations that spans the entire age of the universe. The detection of gravitational waves has also revealed the extent to which black hole collisions contribute to the overall energy budget of the universe. While electromagnetic radiation from stars dominates the visible energy output of most galaxies, the brief bursts of gravitational radiation from black hole mergers can temporarily exceed the electromagnetic luminosity of all stars in the observable universe combined. This energy, invisible to conventional telescopes but detectable through its effects on spacetime geometry, represents a significant component of cosmic energy flow. From the perspective of cosmic evolution, black hole collisions serve as both chroniclers and agents of change. They record information about the stellar populations that created them, the dynamical processes that brought them together, and the gravitational physics that governs their final merger. Simultaneously, they influence their cosmic environment through recoil effects that can eject merged black holes from their host galaxies, through gravitational perturbations that affect nearby matter, and through the gravitational waves that carry energy and angular momentum away from the merger site. The philosophical implications of black hole collisions are as profound as their astrophysical significance. These events occur on scales of space and time that completely transcend human experience, yet they are governed by the same physical laws that operate in terrestrial laboratories. The mathematics of general relativity, developed through human thought and tested through earth-bound experiments, accurately predicts the behavior of objects so massive and compact that they distort the very fabric of reality. This universality of physical law suggests a deep unity underlying the apparent diversity of cosmic phenomena. The same principles that govern the fall of an apple on Earth also determine the orbital decay of binary black holes billions of light years away. The gravitational waves that stretch and compress our detector arms by distances smaller than atomic nuclei carry information about events involving masses millions of times larger than the Earth, moving at speeds approaching the velocity of light. Black hole collisions also illuminate the relationship between information and entropy in the universe. According to our current understanding, the detailed quantum information that fell into each black hole over its lifetime is effectively lost to the observable universe, hidden behind event horizons that prevent any information from escaping. The merger of two black holes represents a moment when vast amounts of information about stellar nucleosynthesis, planetary systems, and perhaps even biological evolution disappear from the cosmic record. Yet this apparent loss of information creates new possibilities. The merged black hole, characterized only by its mass, electric charge, and angular momentum, represents a kind of blank slate in the cosmic memory. Its future evolution will be determined by new interactions with its environment, new accretion episodes, and potentially new mergers that will create entirely novel combinations of mass and energy. The temporal perspective of black hole collisions spans scales that challenge human intuition. The inspiral phase may last millions of years, during which entire species could evolve and go extinct on distant planets, while the black holes slowly spiral together. Yet the final merger occurs in milliseconds, releasing more energy than all the stars in a galaxy during that brief moment. This juxtaposition of cosmic patience and sudden violence reflects the dual nature of gravitational interactions, weak enough to be overcome by electromagnetic forces on small scales, yet inexorable over cosmic distances and times. The spatial scales involved are equally impressive. Black holes themselves may be only kilometers across, yet their gravitational influence extends over thousands of light years. The gravitational waves they produce when merging propagate throughout the observable universe, carrying information about the collision to every corner of cosmic space. A single merger event creates disturbances that will eventually pass through every galaxy, every star system, and every planet in the visible cosmos. This cosmic reach of black hole collisions demonstrates the fundamental interconnectedness of the universe. No event, no matter how distant, is truly isolated from the rest of cosmic evolution. The merger of two black holes in a galaxy billions of light years away will eventually influence the motion of every particle in our solar system as its gravitational waves pass through Earth. The effect is immeasurably small, but it illustrates how the universe forms a single interconnected system where every component influences every other component across vast distances and times. The study of black hole collisions also reveals the universe's extraordinary capacity for precision and beauty. The gravitational wave signals from these mergers follow mathematical patterns of stunning elegance, with frequencies and amplitudes determined by equations that capture the deepest insights into the nature of space, time, and gravity. These equations, first written down on paper by human mathematicians, accurately predict the behavior of objects operating at the very limits of physical possibility. This mathematical beauty extends beyond the equations themselves to encompass the entire phenomenon of gravitational wave propagation. The waves maintain their coherence across billions of light years and billions of years, arriving at Earth with frequency patterns that precisely encode information about their distant sources. They represent perhaps the purest form of information transmission in the universe, carrying news of cosmic catastrophes through the medium of space-time geometry itself. The cosmic perspective on black hole collisions ultimately reveals them as natural expressions of the universe's fundamental tendency toward increasing complexity and organization. What begins as random fluctuations in the density of primordial matter eventually evolves into stars, galaxies, and planetary systems through the action of gravity. Black holes represent the ultimate expression of this gravitational organization, objects so compact and massive that they approach the theoretical limits imposed by general relativity. When black holes collide, they demonstrate the universe's ability to create phenomena that transcend the individual components involved. Two separate black holes, each representing the collapsed remnant of a massive star, unite to create something new, a more massive black hole whose properties cannot be simply predicted from its progenitors. The merger process itself generates gravitational waves that reveal new aspects of space-time physics and provide tools for exploring cosmic evolution. From this perspective, black hole collisions are not merely destructive events, but creative processes that advance the universe's ongoing exploration of physical possibility. They push matter and energy into configurations that test the boundaries of known physics, while simultaneously providing the tools needed to study those boundaries. They represent both culmination and continuation, the endpoints of stellar evolution, and the starting points for new gravitational phenomena. As our understanding of black hole collisions continues to evolve through gravitational wave observations, we gain new appreciation for the universe as a dynamic, interconnected system, where the most extreme events illuminate the most fundamental principles. These collisions remind us that we inhabit a cosmos of extraordinary richness and complexity, where invisible objects dancing in distant darkness can reveal profound truths about the nature of existence itself. In the end, black hole collisions embody both the universe's capacity for violence and its inherent beauty. They represent moments when the cosmos demonstrates its most extreme capabilities while simultaneously following mathematical laws of perfect precision and elegance. Through their study, we learn not only about black holes themselves, but about the deep principles that govern all cosmic evolution, connecting us to the fundamental processes that shaped the universe we inhabit and will continue to shape it long after our own species has passed into history. As our journey through the cosmos of colliding black holes draws to its close, we find ourselves changed by the perspective these invisible titans have offered us. We began in darkness, contemplating objects so extreme they seem to exist at the very edge of possibility. We end in light, not the familiar light of stars and galaxies, but the profound illumination that comes from understanding our place in a universe far stranger and more wonderful than previous generations could have imagined. Black hole collisions represent the ultimate expression of cosmic choreography, dances performed by objects so massive they bend the fabric of reality itself, yet so precise in their motions that they follow mathematical laws of perfect elegance. These are not chaotic crashes, but gravitational ballets, played out over millions of years and culminating in moments of such intense energy release that they briefly outshine all the ordinary matter in the observable universe, though they do so not with light, but with ripples in the geometry of space and time themselves. In the whisper of gravitational waves detected by our most sensitive instruments, we hear echoes of events that occurred when the universe was young, when the first generation of massive stars lived brief but spectacular lives before collapsing into the black holes we observe merging today. These signals connect us directly to cosmic history, carrying information preserved across billions of years and billions of light years in the most fundamental language the universe speaks, the curvature of space-time itself. The story of black hole collisions is ultimately a story about cycles, the recycling of matter and energy that governs all cosmic evolution. Stars forge heavy elements through nuclear fusion and scatter them through space when they die. Black holes represent a different kind of recycling, converting matter into pure gravitational energy that propagates across the cosmos, carrying news of distant catastrophes to every corner of the observable universe. These collisions also reveal the profound interconnectedness of all cosmic phenomena. A merger that occurs in a galaxy billions of light years away eventually influences the motion of every particle in our solar system, as its gravitational waves pass through Earth. The effect is immeasurably small, but it demonstrates that the universe forms a single interconnected system where every event influences every other event across vast distances and times. What makes black hole collisions so remarkable is not just their extreme violence, but their capacity to create beauty from destruction. When two black holes merge, they generate gravitational wave patterns of mathematical elegance that reveal the deep symmetries governing the behavior of matter and energy at the limits of physical possibility. They transform the apparent chaos of cosmic catastrophe into ordered information that advances our understanding of fundamental physics. The detection of gravitational waves has opened an entirely new sense to human experience, the ability to feel the universe trembling as distant cataclysms unfold. Through these ripples in space-time, we can observe events that produce no light, no heat, no electromagnetic radiation of any kind. We have learned to listen to the cosmos speaking in its most fundamental voice, the voice of gravity itself. As we look toward the future, the dance of giants will continue across timescales that dwarf human comprehension. The collision between our own Milky Way and the Andromeda Galaxy, destined to occur in roughly 4.5 billion years, will bring together their central supermassive black holes in a merger of unprecedented scale. Future generations of gravitational wave detectors will observe such events throughout the observable universe, revealing the hidden population of black holes that has shaped cosmic evolution since the first stars began to die. Yet, even as we contemplate these vast futures, black hole collisions remind us of the patience inherent in cosmic processes. The binary systems merging today began their gravitational dances millions or billions of years ago, following orbital trajectories determined by the mathematics of general relativity with the precision of cosmic clockwork. The universe operates not in human time, but in its own deep rhythms, where millions of years pass like seasons and billion-year cycles govern the evolution of galaxies and cosmic structure. In studying black hole collisions, we discover that we live in a universe that is both more violent and more beautiful than we previously imagined. These events represent the most extreme possibilities allowed by the laws of physics, yet they unfold according to principles of mathematical precision and elegance that suggest deep order underlying apparent chaos. They remind us that even the darkest objects in the cosmos participate in patterns of extraordinary grace. The gravitational waves that carry news of these distant collisions to our detectors also carry a deeper message, that the universe is not a collection of separate objects, existing in isolation, but a unified system where every component influences every other component through the invisible threads of curved spacetime. We are not observers standing outside this system, but participants within it, connected to the most distant galaxies and the most ancient events through the gravitational field that permeates all of space. As black holes spiral together in their final moments, they demonstrate the universe's capacity for transformation. What appears to be an ending The collision of two compact objects reveals itself to be a new beginning. The merged black hole carries forward the mass and energy of its progenitors, while discarding the details of their formation, creating a fresh start in the ongoing evolution of cosmic structure. This capacity for renewal in the face of apparent destruction offers a profound metaphor for the nature of change itself. Black hole collisions show us that even the most violent transformations can produce outcomes of unexpected beauty, and that endings often contain the seeds of new beginnings. They remind us that the universe is not a static museum of fixed objects, but a dynamic, evolving system where change is the fundamental constant. In the end, the Dance of Giants reveals black holes not as cosmic monsters to be feared, but as essential participants in the grand symphony of cosmic evolution. Their collisions write new chapters in the ongoing story of how matter and energy organize themselves into increasingly complex and beautiful forms. They are both the culmination of stellar evolution and the starting points for new gravitational phenomena that will shape the universe's distant future. As we close our exploration of these cosmic encounters, we carry with us a new appreciation for the universe as a place where the most extreme violence can coexist with perfect mathematical beauty, where invisible objects dancing in distant darkness can reveal fundamental truths about the nature of existence itself. The gravitational waves from black hole collisions will continue to wash over us, carrying their ancient messages across the cosmos, reminding us that we inhabit a universe of extraordinary richness and complexity. In the gentle ripples that stretch and compress the space around us by distances smaller than atomic nuclei, we feel the pulse of creation itself, the rhythm of matter and energy dancing to the deepest laws of physics across scales of space and time that dwarf human imagination. The Dance of Giants continues, and through our gravitational wave detectors, we have earned the privilege of witnessing its most spectacular performances. The black holes may be invisible, their collisions may last only seconds, and their effects on our daily lives may be immeasurably small. But in their brief moments of visibility through gravitational waves, they illuminate truths about gravity, spacetime, and cosmic evolution that will reshape our understanding of the universe for generations to come. They remind us that we live not in empty space, but in a dynamic, living geometry that carries the stories of distant worlds in its very structure. And so, as the gravitational waves from ancient collisions continue their journeys across the cosmos, eventually reaching Earth as faint whispers of space-time itself oscillating, we are reminded that the universe is not only vast beyond comprehension, but intimately connected in ways that transcend distance and time. The Dance of Giants has been choreographed by the fundamental forces of nature, and through our newfound ability to detect gravitational waves, humanity has become both audience and participant in this cosmic performance. In the quiet moments between detections, as our gravitational wave observatories wait patiently for the next signal to arrive from the depths of space, we can rest in the knowledge that the universe moves with grace as well as power, that even its most violent events follow patterns of mathematical beauty, and that change, no matter how dramatic, is not destruction but transformation. The universe's way of exploring new possibilities written in the curvature of space-time itself. The Dance of Giants will continue long after our own species has passed into cosmic history. But for now, in this brief moment of cosmic awareness, we have the extraordinary privilege of witnessing these hidden performances, of feeling the universe tremble with the echoes of distant collisions, and of understanding, however dimly, our connection to the vast gravitational web that binds all of existence into a single, magnificent whole.